started with, we saw evolution of CAD, different CAD tools for IC flow in terms of ASIC, FPGA, and then processor device molding. And then we saw emergence and features of HDL. And then we saw the difference between VHDL and Verilog. Now we need to understand what are those various design methodologies. Okay. So first approach is top-down design approach. So what do you mean by top-down design approach? I just know what's going to be the overall top-level design. Okay. So for that top-level design, I'll identify what are the subblocks that I need to design, and then in order to make the subblocks, what are the leaf cells. So this approach is more suitable when you have a smaller design. Okay. So you'll fix that overall area, and then within that area, you want to identify where you need to put those subblocks, and then where you want to put the leaf cells. Okay. So first you will define the overall top level block, then identify the subblock which requires to build the top level block, and subblocks again will be formed by the leaf cells. And leaf cell is a lower level abstraction. Further, you cannot divide further. Okay. Whereas in bottom up approach, where you will be first designing the leaf cell. Okay. After designing the leaf cell, you will do the macro cell, that is a submodule, and then you will do the top level design. So this is the more suitable approach when you go for a complex design. So when you have a complex design, first I'll be chopping up into a smaller blocks. After chopping into smaller blocks, then I will be building those individual blocks, where the optimization also will be much better as compared to top design approach. Individual cells, where the characterization will be done on individual cell, and then they will build the macro cell, and then they will build the top level. So your optimization will be better, but the time taken for designing on any bottom-up approach methodology will be much higher. Okay, so the design time will be little higher. Okay, but the end result will be optimization will be good. A good example is let us take a 4-bit adder, okay, or even a counter. So you're designing a, let's say, counter. Then you will be designing a T flip-flop. Then you design a D flip-flop and a market. So this is called a leaf cell, and this is the macros, and this is the top level design. Okay, so in the bottom approach, first I will characterize individual NOT gate and D flip-flop. That's what the designer can able to optimize. Then the logic designer will use this, and then will design the macro, and the top level designer will use this macro to design the counter. Okay, so here the optimization will be much better. Okay, the time taken will be more. Okay. So what's VerilogHDL? Already we discussed. It's a hardware description
used to design and document your electronic systems, and it allows the designer to design at various abstraction level. We saw starting from the switch level all the way to the system level, we can able to do it. A single language, it supports development, verification, and synthesis and testing of your. So why do we use Verilog? Here we will be describing any digital system of any abstraction level as a module. So module is a one, is basically your design, whatever you want to do. We call that as a module. So it can be a gate, or it can be a submodule, or it can be a system. So we call that as a module in Verilog. And each of the module will have an interface to the other modules in addition to its description. So we call that as a module. So this module functionality can be of any abstraction level, and then you will be having IOs. So you'll be providing the inputs, and then you'll be getting the output. Thereby you can understand the property of this particular module. Okay. So how I can specify this module? There are two ways to specify this module. One, by if you know the hardware logic to realize this particular function, then you can represent in terms of structural level. We call it as a gate level way of implementing it. So for example, I'm going to design a half adder. Okay. Then I know I require an XOR gate, I require an AND gate. So describing in terms of a logical structure, we call that as a structural representation. This is one way of specifying your module. So there is another way where you will be describing its behavior. So I know only the functionality of this particular block. Okay, only the functionality. So I don't know what is the hardware it's required to implement that particular logic. So I know only the functionality. So in other words, I know only the truth table of this. Then I can describe its behavior. In a program-like manner, we call this a behavioral level representation. So if I give input of these particular values, then how it behaves and how I will get the output. So representing in terms of functionality. Okay. So here the modules are interconnected using nets, which allow them to kind of work with each other. Now this may be connected to another block, okay, block 2, and we call this as a net or a wire. Okay, so thereby you can communicate with these two blocks. Okay, so here we need to understand a module can able to a Verilog in Verilog module can able to represent starting from a lower level abstraction to any abstraction level. And there are two ways of specifying this module definition. One is, if you know the hardware logic, you can represent in terms of structural representation. If I don't know what going to be the hardware, if you know only the functionality of it, just you know the black box and the black box functionality, then you can represent in the behavioral level form. Okay. So what next? Once you have done the design, after specifying the system in Verilog, we can do two things. One is simulating, other one is synthesizing. So in simulating, you will run the program like in your high level language, and where you will be writing a separate test bench, and then you will specify the inputs that are need to be applied, and you need to check the output. Okay, so we call that as a stimulus. We will generate a stimulus using test bench, and another program which you need to run so that you can test the design that you made. Once you've done the simulation, once you verify the logic or functionality, you will be going to the synthesis tool in order to map it to the desired hardware. So it converts your HDL into a netlist, the lower level primitives, and the hardware can be either you can take through an ASIC flow or you can go with an FPGA flow. ASIC or FPGA. So how to design? So using ASIC as a hardware project. When you are going for a very high performance and high packing density is required, then you go for an ASIC. Okay, so when the manufacturer hardware is expected to be used in a large quantity, like processor chips and all, then you can go for an ASIC. Okay, when you use an FPGA, you want to have a very fast turnaround time to validate your design. Then you go with FPGA. So immediately I need to put it in a hardware and then I need to test its functionality, then you will go with an FPGA. Okay. So the mapping can be done in the lab itself using an FPGA kit and associated software. But you need to have a trade-off in FPGA design, especially in terms of performance. So in the last class we discussed the difference between an ASIC and FPGA. So there itself we discussed ASIC is better in terms of performance as against your FPGA. So here we go. These are all the levels of abstraction that we are going to learn in VerilogHDL. Okay, so starting from switch level, then gate level, then data flow level, then behavioral level. So what is the switch level? It is the lowest level of abstraction in Verilog. Here the module can be implemented in terms of switches. Switches is nothing but the logic transistors. Okay, and then storage node and how they are interconnected between them. Okay, so where by this time you might know in your digital IC you might learn the basic inverter logic, right? So here this is the transistor level design, and then I will use PMOS keyword and NMOS keyword as available in Verilog, and then supply 0 and then supply 1. Thereby I can able to model this, okay, using switch level code. It's the lowest level of abstraction. Then you come to the next higher level of abstraction, gate level. So here a module is implemented in terms of your logic gates and how they are interconnected. So most of the primitives are available as a keyword in Verilog. That's why we always start with gate level instead of a switch level. So and then or and then I'm just connecting it to another AND like that. Okay. So now I can able to model at this level by representing the AND gate or gate and an AND gate. So that we call it as a gate level. Okay. So here a module is implemented in terms of logic gates and how they are connected. Then comes data flow. So now when you're going for a little complex system, then when you have thousands of gate, then representing again at the gate level become tedious. So another high level of abstractions where you talk about Boolean level expression directly, right? So where you will be talking, let us say y equal to, just for an example I'm doing, a XOR b, right? So where I'll be providing A and B inputs, and then I'll be monitoring the value of Y continuously, right? So I'll be able to design by specifying the data flow. So provide the information of input and then see what is the output. There I can still optimize, still I can do it in a much better way for a complex system. Where coming to the behavioral level, it is the highest level of abstraction in Verilog. Here a module is implemented in terms of algorithm. Okay, so that means I don't have any idea about the hardware logic. I know the black box and how it works. Then I will do a behavioral level description, the highest level describing in terms of algorithm. Okay, how it works. So these are the different levels of abstraction in Verilog. Okay, so that we are going to learn one by one.